In this video, we're going to discuss the mechanisms involved with current flow through a semiconductor device. We can break the current flow in a semiconductor down into two different components corresponding to two different force mechanisms driving the charge. Those force mechanisms are what is known as the drift current, which is a result of the electric field or an electric field creating a force on the charge equal to the charge times the electric field. And the second component is known as the diffusion current. The diffusion current is the result of a difference in carrier concentrations and the net random movement of charge from an area of higher concentration to lower concentration. The total current then, I total, will then equal the current due to drift plus the current due to diffusion. So drift again is the current movement due to an external electrical field forcing the charge to move, and the diffusion component is just due to the natural, almost Brownian motion, random motion of an imbalanced concentration of charge carrier, where the charge carrier through diffusion will move from an area of higher concentration to an area of lower concentration until they're uniformly distributed. As we will see, the rate of flow of charged particles is dependent upon what is known as the carrier mobility. The carrier mobility is a measure of how easily carriers move through the material, and by carriers we mean either holes for hole current or electrons for electron current. It's interesting to note that the hole mobility, or the carrier mobility for holes, is 480 centimeters squared per volt, and electron mobility, or the carrier mobility for electrons, is 1350 centimeters squared per volt. Electrons are almost 3 times as mobile as holes in silicon. Both the drift and the diffusion currents have subcomponents corresponding to hole current and electron current. So we'll break down the diffusion current into a hole current and an electron current. We'll break down the diffusion current into a hole current and an electron current. And depending upon the doping, one may well dominate over the other. But at the very beginning of our study of electrical engineering, we noted that traditional current flow, I, refers to the flow of positive charged particles flowing from a higher voltage to a lower voltage, even though we now know that the positive charged particles are bound in the nucleus, and in fact that it's the electrons flowing from lower voltage to higher voltage. But back before, it didn't matter, because at the device level we couldn't discern the difference between a positive charge flowing in one direction and a negative charge flowing in the opposite direction. But at the level where semiconductors are understood, where we have both p-type and n-type dopants, and thus p-type and n-type charge carriers, we now need to be more specific. We'll refer to both hole current and electron current. We'll see that in some instances the hole current dominates, while at other times the electron current will dominate. We'll first address the concept of drift current. Once again, drift current is a function of, or is the result of, an electric field providing a force on the electrons. We're going to go about deriving an expression for current by calculating the velocity that the electrons are flowing due to the electric field, and then multiplying by the charge density times the charge times the cross-sectional area. So to begin with, the velocity due to drift, we'll call it v sub drift, is equal to mu, the mobility constant, times the strength of the E field. We can deduce that from dimensional analysis. You'll recall that the units of mu were centimeters squared per volt second. And you recall from physics, if not otherwise, that the units of electric field are volts per centimeter, or volts over distance. So we get centimeters canceling one of the centimeters, the volts canceling the volts, and we end up with a distance per time, centimeters per second, which is a velocity term. Now, as I mentioned, we can calculate the current by taking the rate at which the carriers are moving. In this case here, we're talking about hole current. This will be I sub p. And over here, we're talking about electron current, so it'll be I sub n. But imagine charge, whether it's holes or electrons, flowing through the semiconductor device, passing a cross-sectional area of the device. And so the current will be the number of coulombs, or it'll be the number of charged particles passing this surface area per unit of time. Again, we can deduce that we've got the velocity times the number of charges. This is the charge density, so in this case it's the number of holes per cubic centimeter, times the charge, which is coulombs per, in this case, hole, times the cross-sectional area, which gives us then coulombs per second, or amps. We can replace the velocity with mu, the charge carrier, times the electric field. But in either direction, we then can talk about charge density, J. It doesn't look like a J, but that's a J. The charge density of the holes then is just the current divided by the cross-sectional area, which is equal to that. We go through a similar analysis for the electrons, where the velocity of the electrons due to the electrical force is equal to mu sub n, the carrier mobility of the electrons, times the electric field, times the number of electrons per volume per cubic centimeter, times the charge per electron, times the cross-sectional area. And so we come up with the current density due to holes and the current density due to electrons, and the total current density then is the sum of those two, which, coming from here, we can factor out the E, which is constant, we can factor out the Q, which is constant. We get then Q times the charge density times the mobility of that charge carrier plus the charge density of the electrons times the mobility of the electrons. It becomes convenient to then define this term right here. That term, charge times the sum of these, is called the conductivity of the material. And the inverse of that, or E, the inverse of sigma, rho 1 over sigma, is what is called the resistivity of the material. The resistivity then is a measure of the resistance per area, and the conductivity is a measure of the ability to conduct current through the material. And once again, these current densities are current densities associated with drift, and drift is the result of an electric field force applied to the charge carriers. The second force mechanism driving current is diffusion. By natural random Brownian type movement, charged particles will diffuse from areas of greater concentration to areas of lower concentration until the particles are uniformly distributed and a state of equilibrium is reached, where the random movement, you've got as much moving in one direction as you have, net movement in one direction as you have in the opposite direction. Once again, the current density will be broken down into a hole carrier and an electron carrier density. For holes, the current density is equal to negative, and we'll talk about the minus sign here in just a second, negative Q times a value D, and we'll talk about that just in a second, times the derivative of the charge distribution with respect to X. So here we have a plot showing a distribution of charge of holes, where the concentration or the number of holes decreases as you go in the positive X direction. So here, close to zero, we've got a large concentration of holes, and as we move further down, the concentration or the number of holes reduces. So in that sense, the derivative of this is going to be negative. Thus, when we talk about the current flowing, we've got a negative chart or negative sign here times a negative to give us positive, and we expect holes to have a positive charge, a positive flow in the positive X direction. So, we've got this constant D. D is known as the diffusion constant, or the diffusivity of the semiconductor. Once again, it's a characteristic of the type of carrier, whether it's a hole or electron, and the type of material, silicon or some other. A typical value for the diffusivity, the hole diffusivity in silicon, is 12 centimeters squared per second. We're going to compare this to the hole and electron mobility in just a minute, but notice the units here are centimeters squared per second. The mobility constant had the units of centimeters squared per volt second. So this then becomes the charge, or the current density for hole carriers, or p-type carriers. We have a similar expression for electron carriers, only you'll notice that the minus sign is missing. Once again, we've got diffusion, or we've got a concentration of electrons that dies out or drops off as we go in the positive x direction. We need to first of all, the electrons are going to diffuse from a higher concentration to a lower concentration. So the diffusion of the negative charges are going to be going in this direction. But you'll recall that current is the direction of positive charge. So when we talk about I-type current, the electrons are going this way. The current then will actually be going in the opposite direction. The I-type current is in the opposite direction of what the electrons are flowing. So once again, when we look at taking the derivative of the distribution with respect to x, as we go from a higher concentration to a lower concentration, the derivative will be negative. And thus, the current density, the current flowing in this direction, will be a negative current density. Otherwise, the expressions are very much similar, where here we have the diffusivity of electrons times the charge. And once again, the diffusivity of the electrons is much greater than that, almost 3 times greater than that of holes. Let's conclude with just a couple of observations about the carrier mobility mu, which we found in the drift current formulas, and the diffusion constant, or diffusivity d, which we found in the diffusion formulas. Note the differences in units to begin with. The carrier mobility has the units of centimeters squared per volt second. The diffusion constant has the units centimeters squared per second. So per volt brings in the fact, or this is related to the fact, that drift is associated with an electric field. And the mobility is a function of the cross-sectional area per volt per length of time. On the other hand, the diffusion constant is centimeters squared, the cross-sectional area, per time. Diffusion is the longer the time goes, the more diffusion is going to take place. So it makes sense that the carrier mobility is per volt, and that the diffusion constant is just per second. Now, some interesting relationships here. The ratio of the diffusivity to the mobility to the carrier mobility of holes is equal to the ratio of that of the electrons. And in fact, that equals a constant Vt, which is known as the thermal voltage. Now, the thermal voltage is equal to K, which is Boltzmann's constant, times the temperature of the semiconductor in degrees Kelvin divided by the charge constant. So at room temperature, where T equals 300 K, and Boltzmann's constant in the units of joules per degree Kelvin is equal to that, and of course the unit charge in coulombs, which is the MKS units also, is 1.6 times 10 to the minus 19th. So when you plug these values into this expression, you find that the thermal voltage at room temperature is 25.9 millivolts. This thermal voltage is a fundamental value that we'll be using throughout the class as we describe current flowing at a PN junction, or in general through transistors.